Right. Hello, everybody. I'm Andrew Holliday. I'm our Applications Engineering Manager here at Phase3D. And today we're really excited to talk to you about spatter detection, as well as our initial results on really gathering data and metrics regarding spatter during laser powder bed fusion builds using our Fringe Inspection technology. Now, to do that, I'd like to actually introduce Michael Brennan, who is our Commercial Director here at Phase3D, where he leads the commercial strategy and growth initiatives for our in-situ inspection solutions. Now, he spent more than a decade working in the AM industry, helping aerospace, defense, energy, and industrial organizations accelerate their adoption of new manufacturing technologies. This has included commercial leadership at Continuum, as well as at Carpenter Technology, and this is giving him a unique perspective on the entire AM ecosystem, all the way from materials and process monitoring to production qualification and industry adoption. With that, I'll hand it over to Michael.
Thanks, Andrew. Yeah, the original impetus for this webinar was to announce our exciting partnership with the folks at Excel3D, our new resellers in India. And we had such a strong demand for the webinar that we decided to open it up to our US audience as well. So we're excited to have the folks from the United States and Europe who have been able to attend this webinar. And we are even more excited to announce our partnership that we are now available through one of the leading manufacturing resellers in India with the folks at Excel3D. As we see our business growing and scaling, we recognize that the Indian market is growing very fast. And while additive manufacturing is still in its infancy in this particular market, we think that partnering with the folks at Excel3D, we're going to be very set up for success to work with universities and some of the strategic primes that are beginning to adopt this in the aerospace, space, and medical market, which is growing really quickly across India. Just a little bit about Phase3D and our technology and why we think in-situ monitoring is so important. We know that there's outstanding potential for additive manufacturing. We've all heard about the hype of, the ability to have freedom of design, to make parts quickly, on demand, and some of the things that have really been holding us back from taking advantage of those advantages and of the benefits of additive manufacturing is related to inspection and the expensive cost of inspection, and the fact that there isn't a inspection process which is specifically designed for the additive manufacturing system, which is unique in that you are building the material and the part at this simultaneously. So you are in the process of trying to qualify many steps that have been condensed down into one. And what we're realizing is that the market is really eager and anxious to adopt a technology which will bring more confidence to the laser powder bed fusion process and allow more process control and process consistency, in addition to the ability to detect process anomalies in real time. This gives you the ability to terminate builds early, to have a more in-control process and understand your normal process variation along with special process variations, which result in defects or non-conforming parts, all of which is with the goal of increasing productivity and throughput. I talked a little bit about the constraints of the inspection process today in regards to post-process NDE. Things like CT are very expensive, time-consuming, difficult to scale as you scale your manufacturing. The other constraints that are facing the additive manufacturing inspection market today rely on the kind of sensors that have historically been used for in-process inspection and their reliance on AI and ML black boxes. And at Phase3D, we just don't have that because we're actually taking measurements from the process and we're using those measurements to generate powder height maps. And those powder height maps are taken every layer, and the measurements that we capture are calibrated to a NIST gauge block, which allows us to have a very high degree of confidence that the measurements we're taking are consistent and repeatable and accurate. A little bit more about how we capture each of those measurements. So we use a technology known as structured light. And the way that this structured light measurement technology works is it allows us to accurately capture any variations in the Z plane. And we've got some people jumping in. And we use, in order to capture these measurements, we use a projector combined with a camera, and the projector projects structured light across the build platform in a form of a sinusoidal wave. We capture several images as the projector projects its light, and the camera and the projector are synchronized so that we're able to capture the wavelength of the projector and measure any discontinuities or shifts in the wave as the sinusoidal waves are projected across the powder plane. This allows us to capture micron level accuracy in the Z direction and be very sensitive to any changes in the process. We are capturing a minimum of 2 powder height maps per layer, and those powder height maps are captured after recoating and then after exposure. So what we see after recoating is hopefully a perfectly flat surface with just normal variation coming from the distribution of the particle size of the powder and its particle size distribution. And then after lasing or exposing, we're getting a more complex image, which contains, everywhere that the laser has exposed on the build platform, and we're able to measure the depression of those exposures, which can be used for things like correlation for dimensional analysis, or in this case, we were able to measure the top surface roughness of that exposed layer. We'll go into a little bit more detail about how exactly we captured those measurements in some of the later slides. So what does the output of these measurement tools look like? This particular image was captured after recoding. So as I mentioned, ideally we're capturing just normal variation, but what we've realized is when you actually measure it, while it may look flat to your eye, there's a lot more going on your surface. We can see some slight corn rows that are forming here. This is more or less normal, but then we would say this is variation that's within your process limits. However, there's obviously some additional process variation that we're detecting that would be cause for concern and would likely result in intervening on this build, canceling it, taking some form of corrective action. So some of the things that we're able to identify specifically are short feeds, which you can see here on the left side. We've got a short feed of almost 120, that's measuring almost 120 microns in intensity. We've also got a part protrusion, which is causing a welling effect here next to the protrusions, so also a depression of powder. But the bigger defect here is that we've got a part protruding out of the powder bed post-recoating, and it's protruding almost 170 microns above the normal plane, which is a pretty significant protrusion. We also have powder streaks, which are seen here and are across the horizontal plane. And then we've also got recoater hops, which are resulting from this part protrusion where we see the recoater begin to skip and hop across the build platform, and we're able to measure those hops at roughly 70 micron process variation from the normal plane. So I'm going to dive a little bit into this particular case study that we've got that was focused on spatter. There are different types of spatter. We started with doing a literature review, and we found some good papers that were published regarding the different types of spatter that present themselves during the laser powder bed fusion process. And what we found where there were a few different types, and that the largest type were these powder agglomerations, and that these powder agglomerations, based on their large size, were the most likely to have detrimental impacts to quality and to be to create a non-conforming part. So we wanted to start by looking at these powder agglomerations and see if we're able to identify some of these larger spatter events that are occurring in the laser powder bed fusion process. So for this particular DOE, we use 17-4 stainless steel, and we used a total of 144 coupons with a very high packing density in the center of the build plate. And we started building in the bottom left corner, and we built these parts from left to right and from up to down, from bottom to top into the gas flow, intentionally trying to induce as much spatter as we can on this in this far left column, and most specifically in the bottom left corner of the build platform. We did also make some slight power variations in hopes of creating more powder or more spatter around some of these higher global energy density parts. Just going into the experiment, we weren't sure how effective building into the gas flow would be in terms of creating spatter. I think ultimately what we found was that we saw very little spatter effects from the higher GEDs, global energy densities, and the increased laser power, and we saw a much stronger impact from building into the gas flow, and that'll be apparent in the results. So the first thing that we did was we just wanted to see, were we able to detect more spatter particles, or percent spatter? Were we able to detect spatter particles in a specific pixel? And then what does it look like when we define 8 regions of interest around the parts that were built? And did we detect more spatter in the regions of interest on the left side versus on the right side? In order to threshold each of these pixels, we basically set a threshold of a 75 micron deviation from the normal plane, and said if the pixel measured above 75 microns, that was a spatter pixel, and then we measured that as a percentage of the total number of pixels in this region of interest. And what you'll see is that we found an increase, a very large spike in this bottom left corner. And this region 6, there was, exactly as we predicted, a huge 10x increase in the number of spatter particles, which we identified, and percent spatter in this lower left corner. And the next thing we wanted to do was, okay, we've been able to detect that there's spatter over the powder. How will we see that when we inspect the build volume? So we took a similar approach, and we divided the build volume into 9 regions, and we looked at the same metric that we discussed before, percent spatter. Did the pixel measure above a threshold, and which percentage of the pixels in that region measured above that threshold to give us a percentage. And then we also measured a surface roughness across that region, with our hypothesis being that if there is a higher spatter density or higher spatter percentage, then there would be a higher surface roughness in each of these regions. So again, we see a really clear correlation that this bottom left region, where we into the gas flow, when we build into the gas flow, that we see an accumulation of spatter density on this lower left side, almost 2 to 3 times the spatter density when compared to the right column average. So clearly this aligns with the results that we saw earlier, where the bottom left corner of the powder area had a much higher spatter density. And we see this same trend for the surface roughness as well. So the part with the the parts with the best surface roughness ended up being parts 3 and 6 when we measured the surface roughness across the entire region of interest. And then the surface roughness continued to get coarser or rougher as we moved to the left and down against the again, into the gas flow against our build order. So this continues to be on trend for our hypothesis. The last thing that we wanted to look at was some sort of external ex-situ correlation that we could do in order to see if there was any correlation between the in-situ process variation that we were detecting and the results of and final part results. So we did a basic Archimedes density test on the coupons in each of these regions of interest and took the average density across those parts. And again, what we found was this far left column continued to have worse performance, which correlated to the increased surface roughness and the increased spatter density. So, our hypothesis coming into this would have been that increased spatter density will increase surface roughness, which will ultimately decrease density or increase porosity. And we see that when we plot this, that we have a pretty strong R-squared value of roughly 0.8 with a good correlation between our spatter density and our surface roughness, and then our spatter density ultimately to porosity as well. When we plot these all the way across, we can again see the correlation between our in-situ metrics here on the left to the ultimate part performance here on the right. And you can see how you would begin to be able to set upper control limits in your process to say, parts 3, 5, and 8 and 4 were all good, whereas our parts 1, 7, and 4 were off nominal, out of control, out of our process control window. So this is a very basic experiment of one build, but it already begins to demonstrate how some of our customers are using the technology to set upper and lower control limits in their manufacturing process. We can begin to correlate in-situ metrics with ex-situ metrics. This is what we get asked every day. How do you determine that the measurements that you're taking, the observations that you have from your process are correlating or impacting your part performance? And this, in one study with a couple parts and some very basic density measurements, we were able to quickly establish that there is a correlation between the measurements that we're taking and part performance. And there's some lessons learned on the setup and the repeatability of this experiment. So I think we have a scheduled plan to repeat this experiment and revalidate the results and maybe do some additional post-process inspection testing, maybe some CT, possibly some cut and polishing of parts. But for this initial evaluation, we were really pleased with the correlations that we saw, and we're excited to answer any questions that you guys may have about the product, about the case study, about Phase3D in general. Just an opportunity for you guys to ask any questions. I know that I saw a couple questions come through the chat that Andrew was addressing as they came in. I think one was about the resolution, and the XY is about 90 microns. Could you mark gas flow direction and recoder direction on the